Hi everyone, welcome to our work, Cstm, Continuous Spatial Temporal Memory Networks for 4D Cstm segmentation. My name is Meng. I come from Rutgers University. This is a joint work with Duke University School of Medicine. Here is the background for this work. In Cstm imaging, we usually generate a 4D image sequence to evaluate the heart function. To calculate the dynamic cardiac function matrix, we need to segment each image in this 4D image sequence. In this work, we assume that we have the segmentation mask at the middle level and at the ED phase. And our goal is to propagate this segmentation mask to each phase and each slice in this 4D image sequence. In previous methods, we can first estimate the motion field between frames and slices, and then we can wrap the segmentation mask to other frames and slices. However, there are some challenges for this kind of methods. The first challenge is the through-plane motion, which can lead to significant morphology and structural change, especially for the basal and apex regions. The second challenge is the large background variation along the z-axis, as can be clearly seen in column B and C in the above figure. To solve these challenges, we propose a novel method, Cstm, which is a continuous spatial-temporal memory network. Our method is based on the spatial-temporal memory networks used for video object segmentation in natural science. The core idea behind spatial-temporal memory networks is to take segmental frames and the corresponding masks as the memory to facilitate the segmentation of the query frame by query memory matching. From this architecture, we can see that we first use a key encoder to extract the query and memory image features, and then we perform query memory matching in the key image feature space in order to write out the memory mask values. And then we use a decoder to generate the segmentation mask of the query image. In previous spatial-temporal memory networks, we perform the query memory matching at the pixel level. However, in a CMR image, some pixels in the background are very similar as the foreground, and this can lead to the query memory matching inaccurate. In this work, we propose patch-level query memory matching in order to make use of the spatial continuity pair in CMR images. This is because at the image patch level, the background is no longer similar as the foreground. Here are the steps for patch level query memory matching. We first divide the images or the feature maps into patches. Then we search the top k most similar memory patches for each query patch. Next, in matched patches, we perform dense pixel-to-pixel matching through the attention mechanism. In the last step, we write out the memory values according to the matching weights. The second contribution in this work is a multi-scale memory matching scheme, where we make use of the scale continuity. In the key encoder, in two consecutive scales, we set the patch size at the lower scale as 4 times of that at the higher scale. And we always start the query memory matching at the bottom of the key encoder. So after performing patch matching at scale S, we can directly copy the AppK IDs to scale S-1. In this way, we can avoid query memory matching at finer resolution scales. Therefore, we can greatly improve the computational efficiency for multi-scale query memory matching. The last contribution is the 4D inference strategy, where we make use of the temporal and through-plane continuity pair in a 4D image sequence. During inference, we first propagate the segmentation mask along the temporal axis, and then we do the mask propagation along the z-axis. This is reasonable because at the middleware level, the hard anatomy structures are almost consistent in the full character cycle. However, at the basal and apex regions, the hard anatomy structures can greatly vary from time to time. For the experiments, we collected 3 public 4D CineMRI datasets, and we combined the 3 training datasets as our own training dataset. To evaluate the mask propagation accuracy, we use dice score and Hausdorff distance as the evaluation metrics. Here are the results on the ACDC dataset. On average, our method outperforms the baseline methods, particularly for the basal region, which is hard to segment. Our method significantly improves the mask propagation accuracy compared with the baseline methods. Here are the results on the M&M dataset. Again, our method outperforms all the baseline methods. We note that in this dataset, some of the testing data is out of distribution data. Therefore, our method is more robust and can generalize better to out of distribution testing data than the baseline methods. Here are some quantitative results. Here are some results on whole heart and whole sequence segmentation. Thanks for watching.